In this video series, we'll develop the flexure formula used to calculate the bending stress using the Bernoulli-Euler equation with certain assumption. Already we are familiar with the shear force and the bending moment diagram, and how to calculate the value of shear force and the bending moment diagram is known to us. So we'll consider here one cantilever beam, and we'll set up our axis system. The horizontal axis will be the x-axis. The vertical axis will set at this point. The vertical axis will represent as y, and the z-axis is perpendicular to the plane. So we are having a loading here, and the loading is in the xy plane. So all the loads are acting in the xy plane. Let we have one point load is equal to F is acting at a certain point here will be equal to C point. Let's say we have UDL is acting of intensity equal to W from D to point E, and let's say at point F we have a couple is acting of a magnitude equal to C. Because of this loading here, the beam will bend about the z-axis, that is in xy plane we have a bending. So I will show here the deflection position of this beam, and because of this the beam will be get deflected. So you will get a deflected position, something like this, and we have deflection in the same xy plane. So we can measure this deflection from center to center line, and this value of deflection we are also able to calculate. So this deflection is taking place in the xy plane, as well as the bending is also taking place in the xy plane. So this xy plane is also called as the plane of bending. What we observed here is that the bottom fiber is get shortened as compared to the original length, and the top fiber will be in tension because the length of the top fiber will increase. So whenever the member is subjected to bending, then normally on the top fiber we have tension is occurring, and bottom fiber we have compression is occurring. It means that somewhere we have the no stress is acting. That will be called as the neutral axis, which is represented by Na. And since we have a positive value of a stress on the top side and the negative value of the stress on bottom side, it means that the stress is continuously vary. Now the question is that how the stress will vary, and the stress will vary from 0 to positive value, and the stress will vary from 0 to negative value to the bottom fiber. So that is exactly the bending stress formula we are going to derive, and this formula is given by flexure formula, which is given as M by I is equal to sigma bending divided by Y is same as equal to Young modulus divided by radius of curvature. So our objective here is to develop this flexure formula, but this flexure formula is applicable only to pure bending. What is the meaning of pure bending? Pure bending means that section of the beam where we have a bending moment is present, but the value of the shear force will be equal to 0. So if any section where we have purely the bending is moment is present but the shear force is 0, that will be called as pure bending. To develop the concept of pure bending, I will take one simple example of a simply supported beam with the two load acting at the ends, and we have two support in between them. That is, we are considering here the overhang beam. So let's consider here one beam, that is the beam AB, and let's say this beam has two load is acting, that equal to W on end A and W on end B, and the beam is supported at C as well as D. From the left hand end, the support C at a distance equal to L. From the right end, the support at distance equal to L, and the distance between the two support, let's say, equal to L. So we can very well develop here the shear force diagram and the bending moment diagram, but before this we must find out here what is the reaction at C and the reaction at D. Now this reaction at C and the reaction at D is same reaction because this one is a symmetrical loading. So if I draw here one vertical line, what we observed is that this loading is a symmetrical loading. So due to the symmetrical loading, the total vertical load acting in a downward direction is 2W is equally divided between RC and RD. So in this case we have reaction RC is equal to reaction RD is same as equal to W. So this reaction RC is equal to W as well as this reaction RD is also equal to W. So I will project here vertical line and we'll develop here the shear force diagram first, and then we'll develop the bending moment. And from this figure we want to conclude what is the concept of pure bending. If you observe the point A, then we have shear force W is acting vertically downward. So from A you have to move vertically downward, and you have to represent here the negative value of the shear force equal to W. Between A and C no shear force is acting, and therefore the shear force is remain constant from A to C. At point C we have vertical reaction is RC, which is same as equal to W. It means that you have to move vertically upward by the same shear force equal to W. So we'll end up at zero shear force at C. So we have zero shear force at exactly equal to C. Then from C to D we don't have any shear force is acting. So from C to D we have zero value of the shear force. So for this region we have shear force V will be equal to 0. Then at point D we have vertical reaction is equal to W. So you have to move vertically upward by the vertical force is equal to W. And again in this case from D to B no shear force is acting, so shear force is remain constant. And then finally we have one point load is acting equal to W, so that is the shear force acting at B, which is the same as equal to negative of W. So positive of W and negative of W, so we have zero value at B. So this one is representing the shear force diagram. So you will get here one rectangle below the zero reference level. So we have shear force diagram is a rectangle. In that case we have bending moment diagram is a triangle but having a negative slope. And from D to B we again get here one rectangle, which one is a positive rectangle of area equal to W into L. This time we have area equal to minus W into L. So a rectangle in the SFD will be replaced as a triangle in the BMD, and we have to continue with the slope as negative for A to C, and for B to D it's a positive slope. And if there is no change in the shear force diagram, then also there is no change in the bending moment diagram. At point A no load is acting from the left side, so the bending moment at A will be 0. Similarly on the right hand side of B there is no load, so bending moment will be equal to 0. Area of the shear force diagram is same as bending moment diagram. We have a rectangle, so in the case of bending moment diagram we will get a triangle, but the slope will be negative. This value of a bending moment will be same as equal to minus W multiplied by L. In the shear force diagram from C to D there is no change in the shear force, so bending moment diagram will remain constant. So our observation is that at C to D we have M value, that is the bending moment is constant value. So this section C to D where we have a shear force is 0 but the bending moment is constant is called as pure bending. So this value is same as equal to minus WL, and the area of the rectangle in between D and B is W into L is positive, W into L and minus W into L, so finally we'll end at 0. So this region here, that is the region under C to D where we have the shear force equal to 0 and we have bending moment is remain constant. This section of a beam is called as pure bending, and our flexure formula is valid only for the pure bending. So if a length of a beam is subjected to constant bending moment and no shear force, that is the value of shear force equal to 0, then the stresses will be set up in that length, that is from C to D of the beam is due to bending moment only, and that length of the beam is said to be pure bending, that is C to D is called as pure bending, and the stresses set up here are called as the bending stress, which are represented by sigma B. This means that between C and D the beam is subjected to constant bending moment only, and this condition of the beam between C and D is known as pure bending or simple bending. So our equation is purely valid when we have shear force is 0 and the bending moment is constant. Now to derive the equation for bending stress, we have to make certain assumptions. Here we want to discuss the theory for simple bending, which is developed by the Bernoulli and the Euler, which one is also called as the Bernoulli-Euler beam theory. And we'll make a certain assumptions here about the elasticity, about the transverse plane. So we'll consider here one rectangular cross section, and we'll consider here one transverse plane, and is subjected to bending. So this one is before bending, and after bending here the beam will be get bent. Bending moment is purely applied above the z-axis, and we have bending will takes place in the xy plane. So let's assume here that we have bending is taking place in this direction. Let's say this value is equal to m, and in this case here about this axis will show the bending will be like. So because of the bending here, the beam will be get bent. So this one is the top plane here. Likewise, we assume here the beam is consist of thin lamina. So this one is the second lamina. So in this fashion, we have the beam is consist of infinite number of laminas. So this figure represent here before we apply the bending moment m. As usual, we'll make the first assumption is that the material of the beam is homogeneous and is isotropic. It means that there is no variation of the Young modulus along the x-axis, y-axis and the z-axis. So value of E remains same. The value of the Young modulus of elasticity is same in tension and compression, and we assume here the material is elastic. When we say the material is elastic, and if we draw a stress versus the strain diagram, then initially from origin to the elastic limit here we have linear relation between stress and strain, and this relation is given by the Young modulus and is same as equal to stress divided by strain. It means that to find out the value of, and this region is same region from 0 to point A, that is up to SYT. Afterward we will get here the necking is formed, that is the yielding is formed. So we are not interested in the plastic region, only we are interested in the elastic region. The third assumption is that a transverse section which are plane before bending, that is this one is a transverse plane before bending, and after bending is also remains same here. So the same beam, when we applied a moment equal to m, that is a bending moment equal to m, then the beam will be get curve shape here, as we have discussed initially also. The top fiber here has a smaller length as compared to the original length, and the bottom fiber has a slightly larger length as compared to the bottom fiber here. And since there is a change in the length, the strain is produced, and once the strain is produced, then the stress is produced according to the equation of a Young modulus which is given as stress divided by the beam is initially straight, and all the longitudinal filaments bend into a circular filament as you observed here. And if you join these edges here, then these two edges will meet at a point here, and this point is called as the center of curvature. And we can measure the radius of curvature with respect to the centroidal axis. So this one is representing the plane which is passing through the centroid. Somewhere here we have a centroid. So this one is a circular arc which is passing through the centroid C. So this one is become the neutral plane or neutral axis. As seen from this figure, we have a radius of curvature is r, and this radius of curvature r is very large value as compared to the width and the height of the section. So this value of r is very greater than the width b, as well as the r is very greater than the depth of the given section. So the radius of the curvature is large compared with the dimension of the cross section. Since here we have assumed that the beam is consist of infinite number of thin lamina, that is a thin layer, and each of these layer is free to expand or contract independently of the other layer, which one is above or below. So all of these layers can be contract or can expand independently, that is the assumption, but in fact that is not true. What we observe is that the layer which is at the neutral axis, which is passing through the centroid, has no change in the length, but the layer which is on the top side, due to the bending moment here, this bending moment is taken as positive because we have a smiley face here, which one is also called as sagging. So this value of bending moment is taken as positive. Then the layer which is on the top side is in compression because the length of the top layer is decreased, and the bottom layer here, that is this complete plane here, that is the bottom layer, which is in tension because the length of bottom layer is increased. So there is a continuous stress variation takes place from tension to compression. If the length will increase, it will be called as tension, otherwise it will be called as compression. So this one will be taken as a negative value and this will be taken as positive value. So somewhere we have a stress equal to 0. That will be called as neutral axis or neutral plane. And this neutral axis or the position of a neutral plane is at a distance equal to r, where r is called as the radius of curvature. So these are the 6 assumptions we are going to use for developing the simple bending equation, which one is also called as the Bernoulli-Euler beam theory. So always remember here that the radius of curvature is very large as compared to the dimensions or the cross section of the beam. Now we have taken here the rectangular. It doesn't mean that our derivation is valid for rectangular. It is valid for all cross section that we are interested. Then the material is elastic. In that case, we have Young modulus will be equal to stress divided by strain. That is a normal strain. So using this simple equation, first we'll develop here what is the strain produced on the top fiber and the bottom fiber, or any distance from the neutral axis. We can generalize the equation of a strain. Then using the Young modulus, we can develop the equation of bending stress, and once we know the bending stress, then we know that the force will be same as equal to bending stress multiplied by area, and moment is defined as the force multiplied by distance y. In that case, we'll develop the equation for bending moment. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.